That's working. You got it right this time. I tried something like this over the weekend and it did not give me the right answer. Well, it does. Actually, it does use your feedback, and your interaction, as part of its training too. So it's alive. That's quoted from Short Circuit, the movie.
Can you just ask it a bunch of questions and say that those are all wrong? Or just like start trying to get should be wrong.
I don't know. All right. Got the person trying to join us. All right, well, it is 5:30, so I'm gonna get started here. So what we'll do today is not to figure out, how ChatGPT gets the answer right, because I'm trying to teach you guys so that you guys know how to get the answer right. So what we'll do today is we are moving along to floating point number representation. And I hope you guys got a chance to pre-read a little bit, because that topic is right after binary comparison. So let me go straight to that portion. So this is the module that we are supposed to be on right now. We are just getting into this today. There's a little bit of math stuff in it. So I hope you guys are feeling a little bit more comfortable with math, especially logs and exponents and stuff like that, because that's kind of what we need in order to understand floating point number representation. So let's go ahead and dive right in. And I rewrote a little bit of it too, so that's why it has a last update date of today or yesterday, because I just recently modified it a little bit. So we'll go ahead and zoom in, and then we'll get started with this. All right, so for some reason, the screen that you are seeing is only a portion of what what it is shown on this side. I'm not sure exactly why. So let me see if I can fix that problem. So I'm gonna have the projector to scan through all the channels and see if it can figure out the best way to render the image. Okay, move on. Try the next one. Nope. All right, let's do search one more time. There we go, but it's still not correct. I mean, this is not the right resolution. All right, let me try auto. Nope, that did not work either. All right, so what I need to do is to change it so that we can see it. Okay, that's better. It's basically not displaying a bunch of stuff on the left-hand side. So just have to make sure that I don't choose anything past a certain point on the left-hand side. So we are getting, okay, that's another person coming in. So apparently a few people got sick, or they got people in their family getting sick. So here we go. All right. So what we're going to do today is to talk about floating point number representation. So the thing is, it's not really that hard. For the most part, floating point number representation is already well explained in a Wikipedia page. And I am struggling to find the Wikipedia page because for some reason, oh, well, okay. So I can just go ahead and explain it. I can go to the Wikipedia page, but we'll just go ahead and do this, just purely based on the description here. So for this discussion, this module focuses on the double precision floating point number. That one, this thing here, was supposed to be a hyperlink, but somehow, the hyperlink feature does not work anymore. So I have to kind of investigate why the tool that I used to render this is not working anymore. The full name is abbreviated to double henceforth, okay? And that is the type name in C++. So in C++, you remember that there's float and then there's double. Float only uses 32-bit, and then double uses 64. Okay? So double has 64 bits, which is the equivalent to 8 bytes. For the discussion of the format, let's use f of I to refer to bit I of a double. So in this case, fi is really just referring to the position of the bit, which does not tell you how to interpret the bit. Okay, so let me just pause here and make sure everybody understands what I just said. F of I is just telling you which bit out of 64 we're looking at, but it doesn't tell you how you're supposed to interpret that bit. Is that okay? All right. So the bit fields are arranged as follows. Bit 63, in other words, f underscore 63, or f subscript 63, is a signed bit. Unlike a signed integer, however, the signed bit of a double is independent and only serves to indicate whether the value is negative or not. When this bit is a 1, it is negative. When this bit is a 0, the value being represented is non-negative. So we do okay. So instead of referring to this as f underscore 63, I'm just going to call this an s bit, sign bit. Are we good? Okay. Are we okay so far? S is just an alias of the most significant bit of a double. Are we good so far? Yes.
So it has to be 1 or 0.
Yes, it can be a 1 or 0. If it is a 1, it means the value being represented is negative. If it is a 0, it means the value being represented is non-negative. But it's not interpreted the same way as the sign bit of a signed integer representation. So we have to make sure that that is not the case. All right, so the next 11 bits, okay, bit 52 to bit 62. These are the next 11 bits counting from the left-hand side. So these 11 bits are basically the exponent of 2. I'll explain later on what I mean by that. So what we'll do is we're going to define E, okay, this is lowercase e, which is the exponent of base of 2. It has a sigma notation that we should be quite familiar with at this point, from 0 to 10. And then you have something here that looks familiar. It is some kind of bit times 2 to the power of I. So it looks like something that we're familiar with, except it is not f of I times 2 to the power of I. It is f of 52 plus I times 2 to the power of I. In other words, everything is kind of shifted by 52 bits. Is that okay? Is that notation understood? So that means bit 52 itself indicates the number of ones, and then bit 53 indicates the number of 2, bit 54 indicates the number of 4, and so on. Yep.
Doesn't the I usually come after, or why is it after?
What do you got to come after?
Like this is F at bit 52 plus
I.
Is that
So the entire 52 plus I is the subscript of F.
it's just
Yeah, so you can see the entire thing here is lower. So this entire thing is a subscript. You can think of this as F open square bracket, 52 plus I close square bracket.
got it.
So 52 plus I, the entire thing describes the position of the bit that we're paying attention to. Is that okay? So you might want to write in your notes, okay, just to be very clear of this notation is trying to say. And then the next sentence says E is not the actual exponent of 2, which is awfully confusing because we just mentioned how the exponent of 2. However, it is an offset amount. The offset amount is 1023. So as a result, the actual exponent of 2 is E subscript 2, and it is E minus 1020. Okay, so let me just get a talk here, and then let me ask you a few questions. Do you think this E here, as defined in this particular sigma notation, can go negative? No, it cannot go negative, right? So that means, then I cannot represent very, very small values, things that are very close to 0. So instead, what I do is I use this E here as a biased number. And then the bias itself is 1023. The value that it is actually representing is whatever this sigma notation is minus 1023. So now with that biased amount, the most negative value for E2 is negative 1023. And then the most positive value of E2 is 1024. Is that okay? So this is how we can use that. This is how we can have a negative range of numbers as well as a positive.
So E has 2 to the 11th values, and then we take away pretty much 2 to the 10th, take away 1.
Correct. Yep. But if somebody is going to ask me, so why don't we just use a signed interpretation of these 11 bits and call it a day? Why do we use a biased approach to do this? My answer is, I have no idea. Go ask ChatGPT. I really have no idea. My only guess, my theory is this is an IEEE standard. And do you know what is IEEE? What IEEE stands for? The International Electrical Engineer something. I cannot remember the threes. I know one is electrical, one is engineering, but I cannot remember the other one. You can look it up. But the bottom line is they probably forgot to let the computer science people to take a look at the standard first. Because the computer science people would have pointed out to go like, hey, you could have just used a signed interpretation. But no, the engineer goes like, no, we can just go for a non-negative number and then we subtract the bias from it. Then it can go both positive and negative. So don't ask me why, but this is the way it works. So we still, okay with bit 52 to 62, those 11 bits. We first look at the 11 bits as an unsigned integer, and then we subtract 1023 from it, whatever that amount is, okay, whatever the difference is the actual exponent of 2. It's a very roundabout way of doing things, but that's how they chose to do it. Yep.
You're meaning the 2 to the I exponent, or just the exponent 2?
Well, it's a magnitude specified. Okay, so because that's one more component. So the last component, and after I talk about all of these, then we'll be clear. So the last component will be the rest of the 52 bits. Because we're going from bit 0 to bit 51, there are 52 bits to this particular part. So this part is called a fractional base 2 mantissa. So I'll explain what is a mantissa next. The actual mantissa is M2. So I'm using M2, the 2 is emphasizing this is in base 2. So M2 is 1 plus, and then we have another sigma notation. And this one, it looks leader off, okay, because it goes from -52 to -1. And then this time we have f of I plus 52, 2 to the power of I. So what does that mean? Okay, so whenever you look at the sigma notation, you go like, I have no idea what you're talking about. Substitute, okay? Plug in the value, okay? Plug in the beginning of value of I into I, and then plug in the end value of I into I. Then you can figure out where do we start? When do we end? Okay, and everything in between is pretty easy. So let's just say that I equals to -52. Okay, so what does it mean when I equals to -52? I is -52. When you add 50 to it, it becomes 0. Right? So that would just be decimating the least significant bit of a double representation. But how do we interpret it? What does it mean? We multiply that by 2 to the power of I, which is -52. So it is a very, very tiny value that you are contributing to the sum. Are we good so far? And then you go all the way to the highest value of I. The highest value of I is -1. So what if we plug in I equals to -1 into f of I plus 52 times 2 to the power of I? Well, if I is -1, then I plus 52 becomes 51. So we are looking at f underscore or f subscript 51, which is bit 51 of the entire number. All right, it's a bit, it's either 1 or 0. What do we do with it? We multiply that to 2 to the power of -1, which is 1/2. Is that okay? So when you look at this sigma notation, ignoring the 1, and just look at this sigma notation, it ranges from 0 all the way to pretty close to 1, possibly. Because if all those bits are 1s, then you are basically adding 1/2 to a quarter, to an 1/8, to a 16th, to a 32nd, to a 64th, blah, 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 blah. So when you add up all of those, it will still be less than 1, but it comes pretty close to 1. Is that okay? So when you add that portion to 1, then you end up with something that looks like 1 point, blah, 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 blah. Is that okay? All right. All right, so the next question now is, now that we have all of these components, okay, the most important components is the sign bit, which is really just a 1 versus a 0. We have E2, which is a number, an integer that can range from -1023 to +1024. And then the third component is M2, which is always going to be in the form of 1 point, blah, 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 blah. Okay, and there are up to 52 digits to the right-hand side of the point. So those are the 3 components. So how do we combine these 3 components to come up with the actual value of a double? This part explains it. So the value of the double, and f is the bit pattern, is basically the sign bit. Okay, if the sign bit is a 1, then you use -1. If the sign bit is a 0, then you use 1. So that part is kind of consistent with how we treat the sign bit up to this point, times M2, which is always going to be a value at least 1, but less than 2. right? Because it is in binary, it is always 1 point, blah, 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 blah. So the best it can do is to come really close to 2, but it cannot really be 2. And then we multiply the entire thing by 2 to the power of E2. And we already saw how E2 is computed itself. It has a range from negative 1023 to positive 1023. And that's how you read a 64-bit double or double precision floating point number. Are we doing okay so far with the math? I know there's a lot of, oh, which bit is doing what again? But generally speaking, are we doing okay understanding the whole thing is sectioned into multiple parts? I did say that, but how do you know I'm telling you the right information? See how I can turn around the question into another question? That's my special talent. So how do we do that? So if I give you the definition of E, how do we know that the range of E2 is negative 1023 to positive 1024?
ChatGPT will tell us.
You can plug it into ChatGPT, but I'm not sure you can handle the symbols. So you think about this, okay? You think about this part here. We are looking at 11 bits. What happens when all 11 bits go from bit 52 to bit 62? What if they're all zeros? What happens to this sigma? It becomes 0 times some power of 2 plus 0 times some power of 2 plus 0 times some power of 2. So what do you get in the end? Big fat 0, right? So what happens when E equals to 0? What is E2 when E equals to 0? Negative 1023. Very good. So now we have established the least value or the most negative value of E2. What about the most positive value? How big can it get? Well, that happens when every single bit here is a 1. So now you have to think about, okay, so we're adding 1, 2, 4, 8, up to what? What is the largest power of 2 that we're adding in this segment? Well, you look at I can potentially be 10. So we are multiplying to, well, some 0 or 1 to 2 to the power of 10. What is 2 to the power of 10? It's a big number, relatively. It is 1024. Okay, so it's 1024. So we're adding 1 plus 2 plus 3 plus 4 plus 8, 16, all the way to 1024. What is that sum?
2047.
20,000 or 2047. Yeah, that is correct. So that means at the most, E can only be up to 2047. So what is 2047 minus 1023? 1024. So that is how you guys can double check to make sure the tag is telling you the right thing. Not that I'm intentionally trying to lie to anyone, but sometimes, I do kind of say the wrong thing, thinking of the right thing, saying the wrong thing. I'll be a great spy. I'm really intending to be honest and then just garble stuff like that. Totally passive and not lie detector. Yep.
So you said F52 plus I would be a 0.
Say that one more time.
F52 plus I would only be a 0 or 1.
Well, because this is a bit. F underscore something or F subscript something is designating a particular bit in the entire bit pattern of F. And it has 64 bits. Yes, we're designating. It can only be a 0 or 1.
Because it's a bit.
Yeah. And the bit stands for. Why is it spelled BIT? Binary digit. Starts with a B, ending with IT. All right. So for those of you who are more visual and more, you like to look at pictures and stuff like that, I cannot blame you. Pictures, yes, with colors too. So you look up on Wikipedia. In fact, you can just look up double precision floating point number. Okay, there we go in Wikipedia. And there we go. It's pictured and it's colorful. And they give you their own version of how to interpret those bits. They are really saying exactly the same thing. Okay, it's just a different way of presenting. Are we good so far? All right. So when you encounter something like this, okay, something that looks like this, it looks like, it's really ugly. What do? You just have to dig in. You don't just kind of glance past it and go like, yeah, okay, whatever. Okay, you really have to dig in and go like, okay, what does it mean? What are we really adding? Which bit is associated with which power of 2? So the technique that I use, I mentioned it earlier already, is to substitute. Okay, I start from 1 in this case. So you say, what if I equals to 1? Then you're looking at bit 51. And what are we multiplying to that thing? 2 to the power of -1 and negative I, which is 2 to the power of -1, which is the half. So it boils down to exactly the same thing that I told you in the way that I presented exactly the same thing. Are we good so far? So the basic ingredient that you need to understand this is the sigma notation, how we designate a particular bit in a bit pattern, and powers of 2. The rest is just addition or subtraction, because we do have to subtract the 1023 from the exponent. But other than that, I mean, really, it's just, that's all we need to do. So are we good so far with this? All right. So I would really love to say that we are done with double precision floating point number and we can just kind of move on to the next topic, but I can't. Okay. So what I will do instead is to make sure that we can work with this. Okay. So one thing we can do with this particular topic is, okay, TAC, can you show me how to convert a number, okay, in base 10 into a double precision floating point number? That sounds like a fair question, okay? So let's go with a number that is at least easier to work with, because I don't want to have to work out all 52 bits of the fractional part of the mantissa. Working out 2 or 3 bits is going to run, but past that point, it's like, why am I doing this? So you guys can think of a number, okay? So I'll give you a guideline of how you can come up with this number as an example. And the best way to do it is to use a spreadsheet again. So let's go take a look at the spreadsheet. And this one, I'm going to use my local spreadsheet, which is LibreOffice Calc. The spreadsheet is a spreadsheet. I mean, just want to make sure that it's on your screen like that. All right. So we'll just say that, maybe at the most we can go with an 8, okay? And then the next one is always going to be the previous one divided by 2. And we can work all the way down to, okay, that should be good enough, okay? Because I don't want to work with any values less than 1.125. So just tell me which ones you want to be ones, and then we'll just add it up, and that will be the number that we are going to work with. So, okay, do we want any one of 8?
Are we transferring from a floating or a double to a 10?
We are going from a base 10 number to a double precision floating point number.
Okay.
But I want to use one that is relatively easy to do by hand. So I will start. Okay, so I'm going to pick out the first and the last, and you guys can pick out something in the middle. Let's pick out 2 more bits in the middle, and then we'll call it a day. Which, huh? Say again? 0.25. Okay. And one more.
2.
Okay. All right. So we'll add these up. So what we'll do is going to say, we will multiply this to this. And then we just end up with zeros for the ones that are not ones. And then we just add up all of these values. And that is going to be the value that we'll play with today. 10.375, okay? So 10.375 is a base 10 number that I want to convert into a double precision floating point number. Are we doing okay so far with this? All right. All right, so since I'm already using a spreadsheet, I might as well use the spreadsheet, continue to use a spreadsheet. So I just have to be careful where you can see, because for some strange reason, the monitor, I mean, your projector is not showing everything. So I have to be like kind of careful with which part of the screen I'm using.
Did you check out the Windows?
This is not Windows, it's Linux.
Is it? Okay.
Yeah, so, and I don't want to change resolution because Zoom is already recording. If I change resolution in the middle, I'm not really sure whether it can handle it. But on the monitor, it looks good. I mean, everything looks good on the monitor. It's just the projector doesn't seem to like this resolution, which is odd. It is a 1400 by 900 resolution. I've used it before in this class, but today somehow it just doesn't want to work. All right, so the first thing we need to do is to convert 10.375 into a base 2 number. Okay, that should be pretty easy, right? So how do we convert 10.375 into a base 2 number? It's basically staring at you in the face already, but you kind of have to tilt your head a little bit to see.
We start with one, the base raised to the 0th tower, and then work our way up.
Yeah. So basically, the cell C1 is the leftmost digit, and then the cell C7 is the rightmost digit. And then there's a decimal point, which really should be called a binary point because this is not a decimal number. So the binary point would be somewhere between C4 and C5. Does that make sense to you? That does not sound like a computer science class.
Yes.
Because there's a point between C4 and C5. That sounds like Bones, from the TV show Bones, right? The C4 and C5 would be your vertebrae. So you find a hole somewhere between those two vertebrae. That would not be a good thing, right? All right, so we'll go ahead and write out the binary number. Okay, so we'll write out the binary number, and I'm going to use a string representation just so that we emphasize this is not a base 10 number. So it would be 1010.011 in base 2. Okay, so I'm gonna, okay, that works. So are we doing okay so far? Doing okay so far that the binary representation of 10.375 is 1010.011 in base 2. Okay, the 10 part should be pretty obvious because we have a 2, we have an 8, 2 plus 8 is 10. But the fractional part is pretty easy too because 0.01 in binary is 1/4 because 0.1 is a half. So 0.001 is an eighth. So we are adding a quarter to an eighth. A quarter is 0.25, an eighth is 0.125. So when you add up those two, you get your 0.375 back. Are we good so far? All right. So now what I'm going to do is to say, well, if I multiply this whole, can I move this point to the left-hand side? In other words, if I were to change this representation and change it to 101.0011 in base 2, but I still want to preserve the value that I'm representing, what do I need to multiply so that row 10 and row 11 turn out to be represented exactly the same? Yes,
By 2.
multiply by 2. Okay, all right. So if I say, I want to move that point again, so it becomes 10.10011 in base 2. What do I need to multiply this time? 4, because the multiply has to be twice of what I had in the previous row. So now if I do it one more time, okay, so you guys can probably guess what I'm going to do now, is 1.010011 in base 2. What do I need to multiply on the other side? Even 8. Okay. So you look at this and go like, I don't see a pattern. How do we turn this into a program? Because I don't see a particular index thing that I can use in the loop. So the way you do this is you look at the first row, you go like, if I really want the same format, I can also say times 1, right? Yes? Okay. But the other way to say 1 is 2 to the power of 0. Is that okay? And then the other way to look at 2 is 2 to the power of 1. And then the other way to look at 4 is it is 2 to the power of 2. And the other way to look at 8 is 2 to the power of 3. Is that okay? So I'm still preserving the value that I want to represent, which to us in base 10 is 10.375. In other words, row 10 to row 13 are just different ways of representing exactly the same value. Are we still doing okay so far with that? Okay. So I think we got enough to figure out what is E2, what is M2, and also what is S. We now know all the components already. So we'll go ahead and start with the obvious one first, okay, the easy one. What do you think is the sign bit? Now that we know that the value that we are representing is 10 point something, it is non-negative. 0. It's a 0. Very good. Okay, so we say S or the sign bit is a 0. What about E2? Remember, E2's job is the exponent of 2. Assuming that we have a normalized coefficient, which I'll explain later. So
The E is going to be 1.
1 or 3, we'll just call it 3 for now, and then do the conversion later. Okay, so E2 is a 3. And then what about M2? M2 is what we call the mantissa, which is 1.010011. And we have to emphasize this is also in base 2. Are we doing okay so far? Yes.
So E2 is that power on the right side?
E2, yes. E2 is controlling the magnitude on each row. And then M2 is what we call the coefficient.
Which is the left side.
Which is the left side, yes.
And then we just, so when we converted it, we just made it have it only like 1 digit on one side of the.
Yes. So when the coefficient is between 1 and it is less than the base, it is called the mantissa. So the mantissa is basically a coefficient, but it has to meet the requirement that the absolute value of the coefficient has to be between 1, at least 1, but it has to be less than the base. So in base 10, the mantissa has to be between 1 and less than 2. Is that okay? All right. So before, if you look at rows 10 to 12, those are not, they cannot be called the mantissa, but they are simply known as the coefficient. Is that okay? It's just a name to refer to the left-hand side of the multiplication. All right. So are we good so far? All right. Okay, cool. So now I need to figure out what is E, because from E2, I can figure out what E is. So can someone tell me how we compute E2 from E from a slightly earlier discussion? The bias amount is 1023. So how do we use 1023 when we want to figure out E from E2? Add it. Very good. Okay, so E is E2 plus 1023. So in this case, it would be what? 1026. Very good. So 1026 is, to convert it into base 2, is 1024 plus 2, and that's it. So that means the E component here in base 2 is going to be 0, 1, 0 as the least significant 2 digits. Oh, okay. I have to be more careful here. And then we have none of 8 16, 32, 64, 128, 256, 512, but we do have 1024. So that's the base 2 representation of E. In other words, I just converted 1026 into base 2. Is that okay?
I thought we only used 1023 for 64 bits.
The bias is 1023, but there are 11 bits for the biased exponent. So the biased exponent itself, which is E, has 11 bits.
It always has 11 bits.
It always has 11 bits. That's what the engineers decided. Yep.
Did you use the summation formula for E whenever you were doing that, or was that?
So are you asking how I got from 1026 in base 10 to this number in base 2?
Yeah. Because
Or why I added 1023 to
I guess from E to E.
from E to the E?
Yeah, I know.
Oh, okay.
I got the other E formula, but like what you were saying, base.
So that has to do with the bias, and I have to go back to my own notes, which is over here. So it has to do with E2 here is E minus 1023. And that's by definition. This is how the IEEE has determined, how we want to represent the value. Yes.
And we're subtracting, I mean, we're adding 1023 because our sign digit's 0.
So we're adding because we know what E2 is. We know E2 needs to be 3, and we want to find out what E is. So you're basically using algebra. This is what we want to figure out. This is known already. And this is a subtraction. So that means if we add 1023 to both sides, then we end up with the unknown on one side. And then the other side becomes E2, which is 3 plus 1023. Algebra. Is that okay? All right, cool. So getting back to my little worksheet here. So now I need to figure out what about the fractional bits, right? This one here is the entire mantissa. The mantissa in base 2 is always going to be 1 point blah, 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 blah. Okay? In base 10, it can be 1 point something, it can be 2 point something, it can be 3 point something, all the way up to 9 point something. So I cannot just say, yeah, we can assume it's always 1 point something. But in base 2, it is always 1 point something. Why do we want to waste 1 bit when we know it is always going to be 1? We don't want to do that. So that means we're only going to store the fractional part, which is 0, 1, 0, 0, 1, 1, and a bunch of zeros on the other side. That would be bit 51 all the way down to bit 0. Is that part okay? Right? So I'm just going to write on this side here, which is the fractional part of M2 is going to be 0, 1, 0, 0, 1, 1, and a bunch of zeros after that, because I have to make sure the entire thing has 52 bits. But I know the leftmost part has to be 0, 1, 0, 0, 1, 1, because it is the fractional part of the mantissa. Are we doing okay so far with this? We're just moving. I mean, all we are really doing is moving zeros and ones around a little bit. Okay. So, okay. So I think we got all the components now. So let's go ahead and take a look at what do we get when everything is kind of put together. The most significant bit, which is the sign bit, is a 0. We figured that out already. The next 11 bits is E, which we have also figured out here, which is 1 followed by a bunch of zeros and then a 1, 0. Okay, so we have 1, 1, 2, 3, 1, 2, 3, 4, 1, 0. Okay, let me just count because I think I might have counted incorrectly. There should be 11 bits here. So we want to count 1, oops. I have to move the cursor here to count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, there's a space in between. Nope, I actually got it wrong. I think I'm missing a 1 here. I'm missing 1 bit here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'm missing a 0 in between. So there we go. Okay. Let me do one more count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, very good. I'm convinced now. Okay. So those are the 11 bits of E, which is E2 plus 1023 for the binary representation thereof. The rest of the bits are the fractional bits, right? The fractional part of M2, which starts with 0, 1, 0, 0, 1, 1, and then the rest with all zeros. So this part would be 0, 1, 0, 0, 1, 1, and a bunch of zeros. Okay, so I'm just going to say they're all zeros after that. Is that okay? So this is my claim, and I'm saying this bit pattern here, which is 0, 1, 0, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 1, 1, and then all zeros after that. These 64 bits arranged in this particular order is going to represent 10.375. Yes?
Maybe it's a stupid question, but why do we even need to sign it?
Because what if I want to represent negative 6.25?
Well, isn't that first one, the one in that position 62 kind of indicative of?
This one. That's how I signed it. I'm not sure what you mean by.
I'll just keep this.
Okay. Yeah, because the magnitude, the rest of it, this part here only specifies the magnitude. It does not specify which side of the number line. This bit specifies which side of the number line. Yep.
So the number was negative 10.375, and we just changed, signed it to 1.
Yep.
Is that
Exactly. Yeah. If I change that most significant bit, which is bit 63, from a 0 to a 1, then I would be representing 10.375. That is. Okay, but we have one big question here, because I can be doing all this stuff and just go like blah 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 and come up with a bunch of zeros and ones. But how do you know this is right? So how do we check this? I mean, we can go back to all the steps, double check everything, but that's going to be not very effective, because if I made a conceptual mistake, I would have made exactly the same conceptual mistake again. So it would probably come up to the same wrong result. So I'm going to test this using a program, okay? Because I think I can trust the C compiler. I think I can trust the math code processor in the computer, and I think I can trust libc, which is the C libraries responsible to do all the printing, conversion, typecasting, and stuff like that. All right, so that's what we're going to do. We're going to write a program to double check this, okay? So that's what we'll do. And let me see, where can I get a terminal? This time it's easy because, oh, I know what to do. Well, maybe. Nah, I think I'm going to use a terminal. And I have no idea where the terminal is. There we go. Okay. Make it a little bit bigger so we can all see. And I promise you, I will only use things that you already know in C++. When you hear me say something like that, what does it mean? It probably is something that really is technically in the scope of CISP360, but it'll be combined in a way you go like, what? Okay. So we'll write the program first, and then we use GDB, the debugger, to actually help us, finish this whole thing. Okay, so we'll go ahead and just go to the temp folder. And write this code. So we'll call this test.c. And that's all it does. And can't include stdint.h because I want to specify the width of my integers. And this is one great way to do it. Int main, there we go, uint 64_t. So this means I want an unsigned 64-bit integer as a type. And we'll call the variable x here. X equal to 0, because if I don't do this, the compiler is really smart and it will optimize the variable out of existence. So we'll do this, and then we'll say return 0. That's it. That's the entire program. Then you go like, nowhere in this program am I referring to double or type conversion or C in or C out. How is that going to help me? Well, the magic is all going to be in GDB. Okay. So I'm looking at the time. We got plenty of time, so I'll go ahead and take row first, while some of you are going to ponder how this program is going to help us. So we'll go ahead and do row taking. This time I do not have the QR code we have prepared, so we're just going to do it the slightly more old-fashioned way. And I'm going to recycle the one from the 14th. And we'll say send to copy to. All right, so give it a little bit of time. All right, not yet. Because what it does is it started a batch process to import a file or import a quiz. Okay, you guys can all see this now. It has the same passcode as last time, but the date is not going to let you do it. So let me change the date first. So today is what? The 21st. And the QR code doesn't work anymore, so don't do it. It's the wrong link. So the access code, let's change it to just double. Okay, that kind of makes sense. And I'll give you guys until, what time is it now? 20, okay, so 6:40 p.m. That's plenty of time. All right, so save. So if you refresh now, you should see the row taking activity called 20230221 row at the end of the module. And then the passcode, the access code is double. So the moment you get this done, you can now start to ponder again, how that little program can get the job done. Yes.
Gonna input the numbers that you have written out, and then you're going to push it to try and typecast it into a double.
Yes, so typecast is definitely in the scheme, but how am I going to typecast it? That is the tricky part. So are we okay with the row taking activity, or okay, I can see some of you are still on the mobile device. Let's kind of, oh, most of you are done. Excellent. So we can now move on. All right, so moving on to this program here that looks like, this is not going to get the job done. So we'll go ahead and do a gcc-g-o test.c. It just compiles the program with debugger information. And then we do a gdb test here. So now we are in the program. I'll put a breakpoint on line 8, which means I'll just make the program pause at that point, run the program, and say, okay, what is x right now? X is 0. That's hardly surprising, right? Because that's how I initialize the variable x to begin with. So now the next question is, Then what do? Well, the first thing is we want to enter the entire bit pattern into here. Okay, but when you look at the bit pattern, you go like, that is not going to be, that's going to be a pretty, tricky because there are a whole bunch of zeros here, and I did not actually specify all the zeros. So this is where you want to learn base 16, okay, or hexadecimal digits or hexadecimal numbers, because I can convert this into a base 10 number, but that's going to take a long time too, because conversion between base 2 and base 10 involves division, mod, that sort of stuff. And it's going to be a pretty long number too. So it's not going to be working out too well. So what I'll do instead is I'm going to use hexadecimal. So in hexadecimal conversion, the way we do that is we look at the bit pattern 0000 and say, in hexadecimal, it really is just 0. We look at the bit pattern 0001, okay, 0001, and we just say, that's also just 1, and so on. Okay. So as you probably can guess, okay, this is not the way I would like to do it, because this means I'm going to do the conversion by hand. Why do I want to do the conversion by hand? So instead, I'm going to use formulae in Excel, not LibreOffice Calc, to do this whole thing. So row is telling me the row number, which is 1 oriented. So this is going to be row 5, but the actual value I want is 2. So I have an offset of 3. But this is going to be, okay, let me show you. This is just 2, which is the right value, but I don't want it as a base 10 number. I want this to be a base 2 number. So there's a function called dec or decimal to bin, which is binary, and that will convert it into a base 2 number. But I want it to have 4 digits. Let me see how to specify the 4 digits. So we'll go to the browser. Instead of asking ChatGPT, we'll do it by hand. So we'll go for bin, dec to bin in LibreOffice Calc. All right. So I want to see if it has a width specification. Yep, it has places. So I can now specify 4 places. So we switch back to this spreadsheet, and then we specify comma 4. Voila. Nice. And we want to go all the way to base 15. So we have all the bit patterns now. From 0 to 15 in decimal, or from binary, it is 0, 0, 0, 0, all the way to 1, 1, 1, 1. Are we good so far? So now on the other column, I can spell each one out by hand. But once again, why do I want to do that, right? So can anyone guess what is the name of the function to do something like this, but converting into base 16? So let me show you the equation here first, okay? The equation so far that we have is dec to bin. So what do you think I can use here? Dec to hex. Hex stands for hexadecimal. So I can use exactly the same thing, which is row number minus 3. So it becomes 0 oriented. And from here, bing, done. Oh, did anyone try to use ChatGPT to do the hexadecimal conversion? I can do that later. That should be kind of fun. Okay.
What is the row minus 3 do?
Say that one more time.
The row minus 3 in the deck to hex, like within the parameter.
Within the parameter,
Yeah.
because the row number is going to give me 3 for this particular cell, but it really is representing 0. So I have to subtract 3 from the offset.
Okay, so you're calling back whatever.
Yep.
Okay.
Yep, because I somehow just chose to start with 0 here.
Okay.
Yep. Okay, so this is base conversion right here. If you see 1011, the hexadecimal digit is going to be a B. No multiplication, no division, no remainder. It's just table lookup. Isn't that cool? So as it turns out, every time we do a base conversion between two bases, where one is the power of the other one, it's just a table lookup. 16 is the power of 2, so it's a table lookup. Has anyone heard of base 64? Okay, so base 64 works exactly the same way because 64 is 2 to the power of 6. So it is also done using just a table lookup. No multiplication, no division, no remainder, super duper easy. Okay, so now we apply this table to the bit pattern that we have here. So the first thing I need to do, okay, is to copy and paste this because I need to arrange the bits in a slightly different way because I want them to be in chunks of 4. So I'm going to erase all the spaces first and then go back here and go like, yep, this is 4, another 4, another 4, another 4, another 4, and then obviously the rest are really just chunks of 4 all the way to the end. So how is that going to help me? Well, it makes it easier to do the table lookup, right? So we have 0, 1, 0, 0, that's a 4, 0, 0, 0, 0, that's a 0, 0, 0, 1, 0, that's a 2, 0, 1, 0, 0, that's a 4, 1, 1, 0, 0, it is a C, and then the rest are all zeros. Is that okay? Does everybody kind of get a handle of how to do a base conversion from base 2 to base 16? All right, so this is why hexadecimal numbers are used in the computer industry because given the hexadecimal number, you can map it to the binary representation just like that. It's a table lookup. But it works the other way around too. Given the binary representation and you want to say, oh, there are too many digits to write. How do I compact this whole thing? Convert it into base 16. Once again, table lookup. Okay. So now we look at this and we go like, okay, I'm just going to go spell it out. This is 0x, which is the prefix to start a hexadecimal number in C++ or C. So this is a 4, 0, 2, 4, C, and then we need a bunch of zeros. How many zeros do we need? How do we figure out how many zeros we're going to need in base 16? The entire thing is supposed to have 64 bits. I figure out the leftmost 4 hexadecimal digits. Yep.
To find out how many zeros you need after this,
Yes.
you take the number of bits with the 64, you divide that by 4. Times the 4.
Yep, 16.
Yeah, so you come out with 16 in that case, and then take the 16 and you subtract 5, I believe it is.
Yep.
Yeah, which you already have, so.
11. Yep, very good. So we need 11 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So once again, the way it works is we need to make up 64 bits. Each hexadecimal digit corresponds to 4 bits. So that means we need 16 hexadecimal digits. The leftmost or the most significant 4 hexadecimal digits are already figured out. So the rest, there are only 11 digits left, and they all need to be zeros. So we're just padding 4024C with 11 zeros in hexadecimal. So now we end up with a hexadecimal specification of 64 bits. Is that okay? All right. So we do this, and then we do a copy and paste. Okay, so Control C is copy, and then go back to my debugger, and then we say set bar x equals 2, paste. There we go. Press the Enter key. So now what I have done is I just transplanted the bit pattern into variable x, which is a 64-bit unsigned integer. So if you were to say print x right now, you're not going to get 10.375 because it is now interpreted as a regular 64-bit unsigned integer. So the interpretation of the bits is just saying, oh, so this is the same thing as the VU thing. Oh, what is VU thing? You guys remember the VU function thing? Okay, so I'm just trying to help you study for the exam. BU is the unsigned value represented by a bit pattern. Okay, so if I want to look it up, okay, at least know where to find it. So this is the BU of the bit pattern using 64 bits, okay, which is not interpreted the right way because this is supposed to be a double. So most of you know typecasting or static cast, okay? But since I'm kind of old school, I'm just going to say a regular cast, which is because in regular C and not C++, this is the best I can do to do typecasting because in regular C and not C++, there is no such thing as a static cast in angle bracket, whatever type, okay? So this is typecasting in regular C. So we'll go ahead and say, okay, maybe this would do the trick, but it doesn't do the trick. It doesn't do the trick because the first thing it does is to figure out the value of X, which is already the wrong thing. It is already interpreting X using the regular unsigned 64-bit integer method. Then it ends up with that gigantic value from the previous line. Then it says, oh, now we want to look at this as a double. So it's preserving the wrong value. So how do we do this trick then? Well, we'll work on this one step at a time. What is this thing here? What is this expression? Yes, it is called the address of. Okay, it is the address of X. X is a variable, it has to live somewhere in memory, so it has to have an address. So the ampersand as a unary operator is address of. So now we have the address of X. Okay. So the address of X has a type. Okay, if I press the enter key here, address of X has a type of, it is the address of a unsigned 64-bit integer. Did that surprise you? I hope not, because that's kind of like, yeah, that's kind of what we expected. So what I'll do is I'm going to typecast the address itself. So I'm going to say, okay, let's take a look at the address, but don't look at it as the address of a unsigned 64-bit integer. Look at it as the address of a double instead. Are we doing okay so far? So you kind of like, you have a house address, and it's residential, it's in the residential district, and UPS says, I cannot deliver there at this time of the day because it's residential. So the supervisor of UPS says, let's override this, okay? Let's just pretend it is the address of a commercial building. Now you can deliver. Is that okay? So when you press the enter key, it goes like, fine, it is not a house, it's not a residential address, it is now a commercial address. But then what do? Then we ask, what's inside the house? What is inside? What is at this address? Okay, so how do we do that? How do we look at the content at a particular address? Okay, first clue, it is not the at symbol, because I think what most people think of is, oh, at, right? No. What is it? What is reversing the effect of the ampersand operator? The star, the asterisk, or the reference, okay? So the name of the operator is the reference, it is an asterisk. So now, magically, we get our value back. So are we doing okay so far with this exercise? As I promised, these are all the things that you have learned already in CISP310, just combined in a way that you might not have been introduced yet. But are we doing okay? Are we doing okay by recombining the operators in this particular way so that we can accomplish what we wanted to do in the first place? Which is, if I were to see this bit pattern as a double, what would be the value represented by this bit pattern? That's basically what it's trying to do. Yep.
Why does double have an asterisk after it? That?
Why does
we like have print double?
in this thing here?
Yes, that one.
That is because without this, it would be I'll be casting the address of X into a double.
Okay.
But I want to cast the address of X into an address of a double. So that's why we need this after.
So you would, without the asterisk, the OX7FFFBF would be a double.
It'll be some, it would interpret as a value. It may not even be valid, but we can give it a try. I mean, nothing is gonna blow up. I hope. Yep, it just looks as some kind of a value. But that's not what we want, because we want to look at the address of X as an address of a double. And then we ask, so tell me what is here, okay? Tell me what is the value, represented by these 64 bits. So is that okay? Yep. Floating point to a decimal.
Binary. Single floating point.
Or convert it the other way around, right? Okay, we can do something like that. But some of the values can be a little bit more difficult to interpret, so I kind of have to think about what to do. So let's do this, okay? We'll say set var X equals 2. We'll start with a C and then give it 0. Let me give it a 3 here, and then we'll say maybe a 4 followed by an 8, and then a bunch of 0. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay. So I have no idea what that is representing. I'm just picking out some bits. I know it is, some bits are here and some bits are over there, but exactly what value this whole thing is representing, I don't know yet. Yes.
To like kind of go back to earlier part of the class, when we were talking about E is defined by the next 11 bits. Why did they choose 11? Is it
I don't
because
know.
they have 12 now?
They could have chosen 12, they could have chosen.
Is it because now you can represent the sign and the E by 3 hexadecimal digits?
There's no particular reason. I mean, it really is, there's no particular reason. It really just changes the range of value that you can represent. So if you have 11 or 12 bits here for E, then you can represent a larger range. So the smallest value closest to 0 would be even smaller, and then the largest value, absolute value, will be larger. So that's the only effect. But somehow they just chose to use, let's pick 11 bits. All right. So now we're going to reverse the whole thing. Okay, we're going to do the whole thing, but reverse the whole thing. Okay, so we'll. What do you think?
Positive.
Negative.
I did not bring my melodica, but it's a 1100.
Yeah.
Yep. Okay. So we'll go ahead and reverse the whole process. Okay, so I'm going to go back to the spreadsheet and just flip around the entire thing. This is what we start with, the hexadecimal number. The first thing we need to do is to turn it into a binary number. How do we do that? How do we go from hexadecimal to binary? It's staring at you in the face right now. Hex to bins, well, you could do that, but you can also just do it manually, right? Yeah, why use a calculator when we can do it manually? It's kind of like asking why think here when there's ChatGPT. So we'll convert this into binary. So it's 1100 for the C, 0000 for the 0, 0011 for the 3, 0100 for the 4, and then what do we have? An 8 here. So that's 1000, and then the rest are all zeros. Okay, so we just say bunch of zeros here. Okay. Okay, now we take this and then we dissect it, but in a different way. So what we first do is to merge, take out all these spaces, because all of these spaces here are just here so that we can divide the entire bit pattern into chunks of 4. I don't need that anymore. Instead, I'm separating the most significant bit from the rest, because that's my sign bit. Okay, so it has significance. By itself, it's trying to tell me something. Then we look at the next 11 bits, okay? So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So right here, we have our E, and then the rest here are all the fractional part of the mantissa. All right, so are we still doing okay so far? You know, because if you look at the shape of everything, I'm doing exactly the opposite way. Is that okay? All right. So now we first identify what the sign is. Okay, the sign is the easy one, it's 1. And then we identify what E is. Okay, so this time is a little bit harder because we have 1 plus 2 plus nothing all the way up to, then we have 1024. Is that okay? So it's 1024 plus 2 plus 1, which is 1027. Very good. Okay. So E itself is 1027. E2 is E minus 1023, and therefore E itself is 4. So now the question is, what is M2? M2 always starts with 1 point. Okay, so that part I don't even need to know why. Okay, but the rest is going to be 0, 1, 0, 0, 1, and then a bunch of zeros. So I'm just going to stop here. Are we still doing okay so far with how I got M2? Because if you look at how we separate the fractional part of M2 to become this part, this time I'm just doing the reverse. I take this part here and say, hey, you know, you really just belong to the right-hand side of the 1 point of M2. So when people bring up the camera, I kind of have to make sure that I step aside. So are we doing okay so far? Doing good? Okay. So now we can work out the math, right? So the next thing to do is to figure out, okay, what exactly is 1.01001? Well, there are a few ways to do this, okay? Because the value that we are representing here is 1.01001 in base 2 times 2 to the power of 4. So you have a few ways to look at this, okay? Because you can always copy and paste it. And then what you do is you shift the point until the exponent becomes a 0. Okay, so you can say, okay, once I shift the point to the right-hand side, the power of 2 is reduced by 1. Does everybody understand why that happens?
Yeah.
Okay, excellent. So now we just have to do it, what, 3 more times? Okay, so copy and paste again. And then the point goes here. The exponent of 2 is now here. And scroll down a little bit. Copy and paste again. 1 more time. All right, so we'll do it really step by step, which is what I would expect you to do in exam 2. All right, 1 more time. So we are moving the point all the way to here. And finally, it is multiplied by 1. So that means, well, whatever that left-hand side is the value, because 2 to the power of 0 is just 1. It does not really change the product in any way. So in this case, we have a half here, we got a 4 here, and we got an 8. Well, no, we got an 8 here. This is a 16. So it's 16 plus 4 plus 1/2. So that's 20.5. It will be negative 20.5 if you look at the value being represented, because the sign bit is a 1, so we have to remember to multiply by negative 1. Yes? No, you don't have to. You have to do it in a way that I know you know what you're doing. So you have to do it like maybe 2 steps and then jump all the way to the end. Yep.
So M2, the last digit to the right will always be a 1.
The digit to the left-hand side of the point is always.
What about so when do we stop counting like the zeros for M2? I'm just confused how we get
M2 is always 1 point something, that something on the right-hand side of the point would be the fractional bits of the mantissa, which is everything except for the sign bit and the exponent. Yep. Right. So is that okay? All right. So that's my claim, okay? So I claim that the X variable, if I interpret it as a double, it's gonna be negative 20.5. So let me just double check my math again, because it would be embarrassing if I just make a simple arithmetic error. This is a half, no 1, no 2, 1 4, no 8, 1 16, 16 plus 4 is a 20, 20 plus 1 half is 20.5. So I think I got that part. So we'll double check. So we switch back here, and then we do the same trick as last time. Remember to put in the asterisk on both sides, and it is negative 20.5. Are there any questions? I sure hope Zoom is recording this entire session correctly.
I heard.
But the whole thing, okay, this entire lecture, okay, this entire lecture can be summarized. If I were lazy, I would just point to Wikipedia. Where's that page? Not this one. We were looking at it earlier. Okay, let's look up double.
Still there.
It's still there? Oh, right, there we go. So if I want to be lazy, I just put a link to here, and this is it. The rest of the lecture is really just a demonstration of, okay, let's start with a value that we want to represent. How do we convert it into all these zeros and ones? And then once that was done, then we reverse the whole process. Let's start with this new pattern here. What is it representing if we look at these 64 bits as a double precision floating point number? So that's pretty much, the entire nature of today's class. I will give you the lab access code because we do have a lab tonight. And you might want to get your calculator ready. If you don't have a calculator, it's okay. You can use spreadsheet, you can use Google Sheet, you can use Excel, you can use all those tools. But you do need something to help you do some calculation. So this is for floating point 1. I think I got everything adjusted already. And also read the instructions. The instructions was here, because I wanted to remind people of log and how to do stuff like that. The access code is double again. Yes, it is double. So I'll go ahead and save and publish. You should be able to get into the lab as soon as you get to the lab. There's a sound problem. Test. Nope, sound is not on.